All right, so in the last video, we got familiar with what the ratio test is. So in particular, if you are given a series, let me throw this in here. If you're given a series, what you do is you take a limit as n goes to infinity of a ratio of subsequent terms. So you take a ratio of an plus 1 over an. You look at the absolute value of that. And ultimately, if that limit of that absolute value of that ratio of terms is less than 1, you get convergence because your series essentially begins to act like a convergent geometric series. On the other hand, when this ratio is greater than 1, you get a divergent series because your series starts acting like a divergent geometric series. In particular, your series starts acting like a geometric series with common ratio greater than 1. Should you get the equal to 1 case, the ratio test is unfortunately inconclusive. Last time we saw an example of two series for which the ratio associated with the ratio test yielded 1 as the limit, and yet one of the series was convergent, one was divergent. So we get an inconclusive result in the equal to 1 case. Okay, so we know what the ratio test is. That does not address the question of how and when is the ratio test used. And there are two types of series that I would like to bring to mind as series where the ratio test works very nicely. And one of these is series where you have some constant to the nth power. Note, this is maybe not surprising at all because these are series that well, take the shape of or sort of look like geometric series. So it ought not be surprising that series that involve r to the n would work well with the ratio test. And indeed, if you take a ratio of r to the n plus 1 over r to the n powers of r downstairs will cancel with n of the powers of r upstairs, leaving just 1 power of r upstairs. Another type of series that works well, or another type of like a piece of a series you can sort of be on the lookout for. Just like you can be on the lookout for r to the n, you could also be on the lookout for factorials. Should your series involve a factorial, the ratio test works quite nicely as well. Why? Because when you take n plus 1 factorial over n factorial, ultimately, the terms downstairs, n times n minus 1 all the way down to 1, are also present above, but above we also have an additional factor of n plus 1. To write this out, just so that we can see this completely, upstairs you have the n plus 1 times n minus 1 times all the numbers down to 1, and downstairs you have n times n minus 1 times all the numbers down to 1. Well, if you cancel accordingly, the only thing that's left over upstairs is a single factor of n plus 1. So, hey, factorials cancel really nicely when you have a ratio associated with a factorial that is like the ratio associated with the ratio test. So let's look at a couple examples so that we can just see this in action. Note this first example, a sum 2 to the n over n. Note that term upstairs is of the form r to the n. Here r is 2, so be it. But ultimately, this is an indication of the fact that we have a term that is at least of the form of something that might work well with the ratio test. So let's try the ratio test out with this series. So to work the ratio test, anytime we want to try the ratio test, we take a limit as n goes to infinity of the ratio an plus 1 over an, absolute value. So this is just the cookie cutter formula for the ratio test. Now, whenever we plug in our terms here, what are we going to plug in? Upstairs, we're going to get the n plus 1th term. Well, the n plus 1th term of our series is going to be 2 to the n plus 1 over n plus 1. And downstairs, the nth term is going to be 2 to the n over n. Okay, now that's a double-decker fraction. So if we keep change flip, we could take this guy downstairs and multiply by n over 2 to the n. And what I'd encourage you to do whenever you do this multiplication, because you know when you multiply fractions, you just multiply across, multiply the tops, multiply the bottoms. I would encourage you to sort of organize your factors above and below. So note, above we have a polynomial factor of n. Downstairs we have a polynomial factor of n plus 1. I would encourage you to put those factors over themselves and sort of to organize your factors of your fractions. It'll make taking the limit a lot easier. We also have exponential factors. Downstairs we've got an exponential factor of 2 to the n. Upstairs we've got an exponential factor of 2 to the n plus 1. So ultimately, our double-decker fraction, after keep changing and flipping, and after organizing our polynomial terms and our exponential terms in a tidy way, we end up in this form. And now we want to take a limit as n goes to infinity. Well, how do we do that? Well, what's the limit of this first term? This first factor. This is an equal heavy rational expression, degree 1 on top and bottom. That's going to approach the ratio of the leading coefficients, which is 1. And now what about this 2 to the n plus 1 over 2 to the n? This is precisely of the form that we looked at previously with this r to the n plus 1 over r to the n. In particular, the n powers of 2 downstairs are all going to cancel, and the only thing that's going to be left upstairs is the 1 power of 2 that remains. So long story short, whenever you apply the limit to this expression, you get a 1 times 2. 1 times 2 is just 2. Now, what does this mean? We just worked through a ratio test. We worked through the limit associated with that ratio that the ratio test is built upon, and we ended up with 2. Well, the limiting value that results from analyzing that ratio tells you whether or not your series is convergent or divergent, depending on what that value comes out to be. So in this case, we got 2 as our limiting ratio. Well, 2 is bigger than 1, and as a result, our series here diverges. So let's write this in one sentence here. So our series diverges since the ratio test yielded 2. So 2 is bigger than 1, and hence our series diverges. I tell you what, I'll throw the 2 is bigger than 1 in here, just so we're all on the same page. Okay, and why did this series work nicely with the ratio test? Well, one of the reasons that it worked nicely was that we had that term that was of the form r to the n. As we'll see, that's something that works nice with the ratio test. So let's look at this next series down below. This next series is, that's a 5 by the way, so this next series is 5 to the n over n factorial. Note, this actually has both of the indicators of the ratio test. This has both a factorial and a factor to the nth power. So this almost certainly is going to work well with the ratio test. So let's play out the ratio test as it is. So the ratio test always begins with a limit as n goes to infinity of an plus 1 over an absolute valued. And so whenever we plug in what our series terms would actually look like in those cases, upstairs we plug in n plus 1 and we get 5 to the n plus 1 over n plus 1 factorial. Downstairs we get 5 to the n over n factorial. Now this is a double-decker fraction, so we keep change flip, and we get n factorial over 5 to the n. Now, multiplying tops and multiplying bottoms here, I'm going to take a similar step to what we did previously and be a little bit tidy in terms of how we arrange our terms, so or our factors rather. So what I'm going to do is take that n factorial and that n plus 1 factorial and put them over one another. So we have those two factorial expressions, one in the numerator, one in the denominator. And we also have two exponential expressions, 5 to the n plus 1 and 5 to the n, correspondingly downstairs. So now when you look at these two expressions, these two things simplify fairly nicely, because with the factorial, the n factorial will cancel completely, and the only thing left downstairs will be that n plus 1 remaining factor from the n plus 1 factorial. And then when it comes to the exponential expressions here, all n factors of 5 downstairs will cancel with n of the factors upstairs, leaving you with just a single factor of 5. So long story short, whenever you look at this limit, the limit is going to be 5 over n plus 1, and we're taking a limit as n goes to infinity here. So as n goes to infinity, the denominator is getting very big, the numerator is only 5, and as a result, this limit turns out to be 0. Okay, what does that mean? Well, that means that the limit associated with our ratio, which came from the ratio test, came out to be 0. And well, 0 is certainly less than 1, which falls in our convergence case. So I'll be very explicit here and say 0 is less than 1, and we can say then in conclusion that our series converges since the ratio test yielded 0. So anytime your ratio test yields a limit for your ratio less than 1, you get convergence. If the limit pops out to be greater than 1, you get divergence. And here were now two examples where we saw the ratio test in action. Remember, the ratio test works really nicely when you see factorials. It also works really nicely with expressions of the form r to the n.